In this video, we are going to apply the Laplace transform to solve this differential equation. I previously solved a differential equation with the right hand side being a polynomial of the first power, which is just t. Here we are going to use the same Laplace transform to solve this one, but on the right hand side we will have e to the 3t, which is an exponential function. So just to recall, the Laplace transform of the derivative. So the Laplace transform of the first derivative, that is y prime of t, this is s times y of s, that is the Laplace transform of y of t minus the initial condition y of 0. Now the Laplace transform of the second derivative, which is y prime prime of t, this is s squared times the Laplace transform of y of t minus s times the initial condition y of 0 minus y prime of 0. These are the initial conditions. Cool. So to solve the Laplace transform, to solve the differential equation, I beg your pardon, we will have to apply the Laplace transform on both sides. So that's what we have been doing. So now let's go ahead and do that. So I'm just going to take the Laplace transform on the right hand side, which is y prime prime of t minus 2 times y prime of t plus 2 times y of t, like this, and this is equal to the Laplace transform of e to the 3t. Laplace transform of e to the 3t, like this. Cool. So using the linearity property, we have the Laplace transform of y prime prime of t is the first one, minus 2 times the Laplace transform of y prime of t plus 2 times the Laplace transform of y of t, and this is equal to the Laplace transform of e to the 3t, like this. So now let's just plug these ones in. So the Laplace transform of y prime prime of t is this. So I'm just going to write that here, which is s squared times y of s minus s times y of 0 minus y prime of 0 minus 2 times the Laplace transform of y prime of t is that. I'm just going to write it here, s times y of s minus the initial condition y of 0, and now plus 2 times the Laplace transform of y of t, which is capital Y of s, and this is equal to the Laplace transform of e to the 3t is 1 over s minus 3, right? So if we can recall, the Laplace transform of e to the at, this is equal to 1 over s minus a, with s strictly greater than a, implying that the Laplace inverse of 1 over s minus a is going to return the exponential function e to the at. So that is what we are just applying here, and we get 1 over s minus 3. Cool. So on the right hand side, we will have to now plug in the initial conditions. Y of 0 is 0, but y prime of 0 is 1. So let's plug that in and simplify our result. So s squared multiplied by y of s minus this one is 0 from the initial conditions. So that is 0, but this one is 1, y prime of 0. So that is 1 minus 2 times s y of s. Right, and now minus, when you multiply that, it becomes positive. So plus 2 times, but this is 0, right? So that is needless if you write that. And now you're going to add this, plus 2 times y of s, and that is equal to 1 over s minus 3. Alright, that is after plugging in our initial conditions. So now let's gather like terms. This y of s, it appeared 3 times on the left hand side. So this one is going to be y of s, which is factorized out, and what is left is s squared minus 2s plus 2. Right, and now this one here is left, and now this is equal to 1 over s minus 1. Cool. So now let's take this one to the right hand side. So y of s multiplied by s squared minus 2s plus 2. This one is equal to 1 over s. It's s minus 3. I'm sorry about that. This one is s minus 3. Terribly sorry. So s minus 3, and this is s minus 3. Shouldn't do math when I'm tired. And now plus 1 on the right hand side. So now cool, so let's isolate y of s by dividing both sides by this guy. When we do that, y of s on the left is going to be 1 over s minus 3, and this is multiplied by s squared minus 2s plus 2, like this, and now plus 1 all over s squared minus 2s plus 2, like this. Cool stuff. So this is what we have. So how best can we are going to use partial fractions for this, but this one, how best can we solve that? So I am going to rewrite this one to look like what we know already before we can take the Laplace inverse. So let me just work this one in few steps. So s minus 3, this is multiplied by s squared minus 2s plus 2. This is partial fractions. We'll do that later on. But this one is going to be 1 over, you can complete the squares here. S squared minus 2s plus 2 can be written as s minus 1 all squared. So s minus 1 all squared is equal to s squared minus 2s plus 1. But we have plus 2, so that means we have to add 1. So adding 1 here, this one is going to be 2. Alright, so in place of s squared minus 2s plus 2, I'm going to replace that with s minus 1 all squared plus 1, which is what we have here. Alright, so now let me clean this one. Alright, so now this is what we have. This is already something that we know. So this one, I can write it as 1 squared. It's already something that we know. So we can easily take the Laplace inverse of this. But this one, we will have to use partial fractions. So now let me switch colors and then we use partial fractions for that. So you see that solving the differential equation using Laplace transforms, we will have to master how to break some fractions down using partial fractions. So 1 over s minus 3 multiplied by s squared minus 2s plus 2 partial fraction, we are going to have a over the first one, this is linear, plus because this is quadratic term, the numerator is going to be linear, so that's going to be bs plus c divided by s squared minus 2s plus 2. Cool. So now the LCM here is the product of the two terms. Now let's divide. So the left hand side is 1 all over s minus 3 multiplied by s squared minus 2s plus 2, like this. So now let's divide. This one divided by this is the quadratic term, so it's going to be a multiplied by s squared minus 2s plus 2, and now plus bs plus c, this is multiplied by the linear term s minus 3. So the denominators are the same. When we multiply by it, we cancel it. Now the numerators will now be the same as well. So that means that 1 is equal to, now let's expand, as squared minus 2as, right, plus 2a. And now expand this, FOIL this one too, is going to be bs squared minus 3bs, right, plus cs minus 3c. Cool. So now let's gather like terms. So 1 is equals to, so we have a plus b, and those are the coefficients of s squared, so group like this. And now what about the coefficient of s? Negative 2a, right, minus 3b plus c, those are the coefficient of s. And now we have the constant term, we have 2a minus 3c, so plus 2a minus 3c. All right, so now let's compare both sides. So we have a plus b is equal to 0. So the coefficient of s squared on the left hand side is 0. There is no s squared here. This is equation 1. We have negative 2a minus 3b plus c, this is equal to 0 as well. Equation 2, the coefficient of s is 0 on the left hand side, right? And now the last one is 2a minus 3c. This one is equal to 1. The constant term on the left hand side is 1. Solving these three equations simultaneously to find a, b, c. So now let's do that. I don't have the values of else, but we are going to solve this one in a different color. Why not? So a is equal to negative b from equation 1. So if a is equal to negative b, guess what? We can plug that into equation 2 and equation 3. So I can call this one equation 4. So if a is equal to b, let's plug it here in equation 2. A is equal to negative b, that means negative 2 times negative b here, minus 3b, right, plus c, and this is equal to 0. So now if we simplify this one is going to be positive 2b minus 3b, that's going to be negative b plus c, and that is equal to 0 as well. So this means that c here is equal to b. You can call this one equation 5. So this is what we get from the fourth equation, that is plugging it into equation 2. Now let's plug the same thing into equation 3. So that means a is equal to negative b. So 2 into a is negative b minus 3c, and that is equal to 1. So that means that negative 2b minus 3c. This is equal to 1. So we can multiply both sides by negative 1. That is going to be positive 2b plus 3c, and that is equal to negative 1. You can call this one equation 6 if you like. So if c is equals to b, we can just plug it here. C is equals to b. So from equation 5, c is equal to b. So in place of b, I'm going to put c. So this one is going to be 2c plus 3c, and this is going to be negative 1. So 2c plus 3c is going to be 5c. 5c is equals to negative 1. That means that c is equals to negative 1 over 5. Like this, we have gotten c. Now that we have gotten c, we know that c is equals to b. If c is equals to b and c is negative 1 over 5, that means that b is equals to negative 1 over 5 as well. So a and b, b and c are the same. Now we have gotten b to be negative 1 over 5. A is going to be negative into b is negative 1 over 5. So that is going to be positive 1 over 5. So there we have our values, a, b, and c. Very easy. So a is 1 over 5. B is negative 1 over 5. That is why they are summing to 0 in the first equation. And then c is going to be negative 1 over 5 as well. Alright, so we can verify that these ones are the correct values of a, b, and c, satisfying all the three equations. So now let's go back to our partial fractions. So our partial fractions, we are going back to our partial fraction here. So 1 over s minus 3 multiplied by s squared minus 2s plus 2. This is equal to what? That is equal to a over s minus 3. A is 1 over 5. So 1 over 5 over s. This is what we have. 1 over 5 over s minus 3. That's the same thing as 1 over 5 times 1 over s minus 3. Like this. Right. And then we are going to have plus bs plus c. Plus bs plus c. So that is going to be minus 1 over 5 times s. Right, so let me write it here clearly for you to see. So it's going to be plus bs, and b is negative 1 over 5 s, plus c, and c is negative 1 over 5. And this one is going to be divided by the quadratic term, which is s squared minus 2s plus 2. This is what we have from our partial fraction here. That is this guy. All right, so cool. So this one is going to be 1 over 5 times 1 over s minus 3. Now this one, you can simplify it. So negative 1 over 5 is common. You can factorize it out here. And now what you are going to have on top is going to be s plus 1 divided by s squared minus 2s. And now plus 2 like this. Alright, so this is what we have after using partial fractions. Cool stuff. So that means that 1 all over s minus 3 multiplied by s squared minus 2s plus 2. This one is equal to 1 over 5 into 1 over s minus 3 minus 3 here minus 1 over 5. And then we are going to have this. So s plus 1 divided by this one, the denominator can be written as s minus 1 as already demonstrated earlier on, s minus 1 all squared plus 1. And this is how the denominator can also be written. So this is what we have. So with this one, we have s minus 1 at the denominator, but we have s plus 1 on top. I would want this one to look like x minus 1 on the numerator as well. So for me to do that, I will have to permit me to just simplify this one to match with what we already know, right? So this one is going to be 1 over 5. I'm just going to write this one all along times 1 over s minus 3 minus 1 over 5, right? And now this s plus 1 on top, I'm going to write it at s plus, so 1 can be written as, you have negative 1 plus 2, right? So negative 1 plus 2 is really positive 1. Then we are going to divide this one by s minus 1 all squared plus 1 like this. So we are now going to split this one into two different fractions. 1 over 5 multiplied by 1 over s minus 3 minus 1 over 5, and then into two fractions, we are going to have s minus 1 divided by s minus 1 all squared plus 1. That's the first fraction. The second fraction is going to be 2 all over s minus 1 all squared plus 1, like this. Now we can distribute with 1 over 5 here. So that is going to be 1 over 5 times 1 over s minus 3 minus 1 over 5 times s minus 1 divided by s minus 1 all squared plus 1 minus 1 over 5. So this one is now going to be minus 2 over 5. Minus 2 over 5. Then we are going to have 1 all over s minus 1 all squared plus 1. So this one is now how we can break this one down. So this one is the same as this guy. Alright, so now let's go back to our Laplace inverse. So it means that here we are now going to take the Laplace inverse of this. So now that we have this one, we are going to take the Laplace inverse of this. So we come back here. Let me do this one in white. So we are going to take the Laplace inverse of y of s. Laplace inverse of y of s. And this is going to be the Laplace inverse of everything here, like this. Laplace inverse of 1 all over s minus 3 multiplied by s squared minus 2s plus 2, like this. And now plus 1 all over s minus 1 all squared plus 1 squared, like this. So that means that the Laplace inverse, this is inverse, so the Laplace inverse of capital Y of s is going to be y of t, which is our solution, and that is going to be the Laplace inverse of 1 all over s minus 3 multiplied by s squared minus 2s plus 2, like this, plus the Laplace inverse of this one, 1 all over s minus 1 all squared plus 1 squared, like this. Alright, so this is what we have. So now let's go down there and now write this. Our solution is going to be the Laplace inverse, right? The solution is the Laplace inverse of this function, and that function has been broken down into something else. So this one has been broken down into something like this. So that's the same thing. So the Laplace inverse of this guy, because that is the same as this, right? Okay, so that is going to be 1 over 5 multiplied by 1 over s minus 3 minus 1 over 5 multiplied by s minus 1 all over s minus 1 all squared plus 1. 1 can be written as 1 squared, why not? And now minus 2 over 5. Then we have 1 all over s squared minus, s minus 1 all squared plus 1, which is written as 1 squared, like this. This is the first one, and now we are going to add that to the Laplace inverse of this guy, right? Plus the Laplace inverse of 1 all over s minus 1 all squared plus 1 squared, like this. Yeah, I hope this is clear. So that is what we have here. Cool. So now let's solve this one. So we can apply the linearity property here. So we have y of t, our solution. This one is going to be 1 over 5, and now the Laplace inverse of 1 over s minus 3, like this, minus 1 over 5, the Laplace inverse of s minus 1 divided by s minus 1 all squared plus 1 squared, minus 2 over 5, the Laplace inverse of 1 all over s minus 1 all squared plus 1 squared, right? And now plus the Laplace inverse of 1 all over s minus 1 all squared plus 1 squared, like this. You see that this one and this one are similar. This one and this one, they are similar. So when you sum them, that is going to, so negative 2 over 5 plus 1 is going to be positive 3 over 5. So y of t is equal to 1 over 5, the Laplace inverse of 1 over s minus 3 minus 1 over 5, the Laplace inverse of s minus 1 all over s minus 1 all squared plus 1 squared, and now plus this one will sum to 3 over 5. because these functions are the same. That was sum to 3 over 5. 5 is not written properly. Then the Laplace inverse of 1 all over s minus 1 all squared plus 1 squared. Now I'm going to do something here. Now we know this, the Laplace transform of e to the at. So let me say e to the at multiplied by sine of bt, like this. This one is going to be what? So this one is going to be b, right, divided by s minus a all squared plus b squared, right? And the Laplace transform of e to the at multiplied by cosine of bt, this is going to be s minus a divided by s minus a all squared plus b squared. So the exponential function multiplied by the sine of bt, a Laplace transform of that is just the Laplace transform of sine of bt, but we are going to shift the s variable by the constant in the exponential function. That means that if you are taking the Laplace inverse of these guys, that is going to return the exponential function multiplied by the trig function. That's what we have here, right? If we are taking the Laplace inverse of this one, we know that we are going to have the trig functions but multiplied by exponential function raised to the power a certain constant. So y of t is going to be 1 over 5. This one we already know this one to be e to the 3t, like this. That's the Laplace inverse of 1 over s minus 3 minus 1 over 5, right? And this one is cosine because we have s on top. This one is going to be cosine, but cosine of what? That's 1 squared. So cosine of 1t, like this. But the s variable is shifted by 1, so that is going to be multiplied by e to the 1t, like this. And this one is going to be what? Plus 3 over 5. Because we have a constant here on top, not the s, that is going to be sine, but sine of what? Sine of 1t, because it's 1 squared, so sine of 1t, but the s variable is shifted by 1. That's suppose that we are going to multiply it by the constant. The constant in the exponential function is going to be 1t, like this. Alright, so now this is the solution. So that means the Laplace inverse of these guys will return these functions here. So the solution to the differential equation is this: 1 over 5 e to the 3t minus 1 over 5, right? This is e to the t times cosine of t plus 3 over 5. And this is e to the t multiplied by sine of t. And this one is a solution to our differential equation. So for simplicity, 1 over 5 can be factorized out: e to the 3t minus e to the t cosine of t, right, plus 3 e to the t sine of t. And this one is the beautiful answer to this differential equation. And you can verify this. I leave this one to you as a homework. You verify that this one is the true solution to our differential equation. Differentiate it for one time and do it again for the second time, and plug that back into the differential equation and see that the left hand side will be equal to the right hand side. So that is how to solve this differential equation using Laplace transforms. So if you find this video helpful, give me a thumbs up and subscribe to Calculus Diaries, and I will come your way again with another problem.